Now we are going to start with new part of this coursework. So now the new part is P, NP, and NP complete and NP add. So we'll discuss what is P, NP, NP complete, and NP hard. This is common notion in computer science algorithms and theory of computation. So first, this computational complexity theory. What is that? It is basically comes in the field of two things: theory of computer science as well as in the analysis of algorithms. So we'll cover this part, analysis of algorithms part we'll cover to see this computational complexity theory. So there are two ways to see the same computational complexity theory. The two ways are theory of computation and analysis of algorithm. Because we are dealing and studying algorithms and analytics part, so we'll just see what analysis of algorithms. So in the algorithms, basically it attempts to solve what computational problems, how they want to attempt and how they solve those problems with some mathematical steps, and what these mathematical steps makes an algorithm. So algorithms are made up of what mathematical steps, and algorithms attempt to solve what computational problems. Then a computational problem, such as some algorithms were designed for that computational problems, could run at computer as a Turing machine or as a some machine, mechanical machine as well. So this we are computer science engineers, so we'll study with computers. So computer will execute what algorithms for some computational problem. Thereafter, what is the main focus of this computational complexity theory? So main focus of this computational complexity theory is to classify various computational problems according to how much resources they use. So how much resources they use, according to this domain, this theory will classify those computational problems. We'll see in detail and you'll understand it better. First, we need to understand what is resource usage. So resource usage means amount of resource that is needed to complete that computational problem. So the amount of resource that is needed to complete that computational problem is resource usage. And examples of resource usage is time for computing by the processor or some device that is computing. So time, how much time it will take, how much time that computer will take. Then storage, that how much memory it requires to store. Then in the previous lectures we had discussed about this single source shortest path implementation. And what we had seen in this slide, we had seen there are four algorithms and they have different worst case complexity. So what is topological sorts complexity? E plus V. And we can say it is an easy kind of algorithm, means it can solve in linear time and it will take only linear time to solve an algorithm. Then disasters binary heap would take E log V. We can say it is a medium complex problem. Thereafter, Bellman-Ford or Bellman-Ford Q-based algorithm would actually take E dot V, means multiplication of E and V, and it, as compared to above two problems, we can say this part is hard and it takes more time to solve. And in this part, we had seen the remarks, three remarks. The directed cycle actually makes problem harder. Means if a graph is there and there is some directed cycle, then this makes problem harder. And additionally, when there is negative weights, so this will make what problem even more harder. The negative weights make problem even more harder, but negative cycle would actually make problem intractable, because negative cycle it's infinite loop. So uh, till it will become minus infinity, you keep on rotating on that negative cycle. So it's intractable problem, it's is non-deterministic. So we'll see and study and discuss about all these problems that are interactable, and this is the main objective of this part. Then deterministic algorithms, what are deterministic and how these are being done, studied. So some of the given computational and inputs are there. In this algorithm, basically you have some fixed input, and when you execute that algorithm, you'll get whether it's yes or no. Means there the steps would be deterministic and there will be no guessing. So there is fixed step and fixed output, and you'll get either yes or no, and will produce some same output whenever there is a particular input. Means in deterministic algorithm, doesn't matter how many time you run that algorithm, if you give the same input, it will produce same output. Then the machine will have the same sequence of states, means same sequence of step it will follow to generate the same result. So it doesn't matter how many time you execute. In the case of deterministic algorithm, it will give you same result. Then state machine. What is state machine? It's basically state of some machine that happens at particular instant of time. Means that state will keep on moving, means from one state to another state to third state to fourth. So it the state machine actually passes discretely from one state to another state. So this is what the property of a state machine or deterministic algorithm. So the input of the entire program, whenever you enter some input, so it will be in some initial state or some starting state. Means this part input was being given. So in the deterministic algorithm, first you have the initialization, thereafter you will have all the current states. So all the current states means there are various steps of the algorithm, and these steps could determine the next states and next steps with a fixed manner. So the current state could determine what will be the next state, and the set of states are predetermined. Means you know it from the starting. Then these are the states which are going to happen in this program or in this code or in this algorithm. Then next we'll see non-deterministic algorithm. So, how this non-determinism starts happening in the algorithm? Simply that the algorithm start doing what prediction or some guessing part. So, it will happen that some of the external states are there, and the input was being taken from that external states. Means external states could be different at different point of time, and it can give you different inputs, and you can have different outputs. Thus the whole algorithm may becomes non-deterministic. Then user would actually gives you input, and this is also non-deterministic. Some global variable could also give you some non-deterministic values. Hardware timer values could be non-deterministic, and random values could also lead to your algorithm to become non-deterministic. Means some random output would be generated every time you have different output. So storage disk data would also go in some inconsistency, and it will produce some non-deterministic results. Then time sensitivity means you have multiple processor. Nowadays you find multiple processor that are writing at a particular data, and different processor are writing on the same data at the same time. So they might create some non-determinism by while writing the data, and you can have multiple writes and multiple inconsistencies on some memory or data. Thereafter you have hardware errors that actually cause some state from to reach to the unexpected way. So there are hardware errors possible that actually leads to some unexpected states, and because of the hardware failure you have some problems in the output, and thus you have an non-deterministic algorithm. Then the order of the processor means the order in which the processor is writing the data may also be varying and different. So it will affect the result. Means you have different result in case of non-deterministic if there is processor is writing in different ways. Then what is determinism and non-determinism? We'll see differences. So we already know what are the advantage of deterministic algorithms. We had already seen minimum spanning tree, shortest path. These are deterministic algorithms, and we are using all these computer and many things, and they are usually deterministic in nature. The most important part is to finding out disadvantage of determinism. So the future was be predictable, and if there is some game theory, if there are some players that want to detect that what would be the future, if the algorithms are deterministic, then they will use some intelligent algorithms, or they use their intelligence brain to detect and predict the future predicted by the future given by the algorithm. Thus the this is disadvantage. And security hacker may hack the key or some value or some thing from the algorithms, because algorithms are predictable and have the fixed future. So it's not a good thing in the game theory and in the security. Then you have some predictability in card shuffling. So there is card was being shuffled and some security key was generated. If the algorithms are deterministic, you can detect what are the card about to happen next, because of the card shuffling is fixed. Secure similarly for security key. Then pseudo random number generators are being used for generating some of the randomness in the algorithm. But the main problem is that pseudo random number generator also uses some deterministic algorithms, so they are not sufficient enough to generate some pseudo random number generation. So what are the solutions? So solution is cryptographically secure pseudo random number generator. So there might be some cryptography that happens and which is not easy to break. So that in that way you can generate random numbers. Then hardware random number generator. So what does mean by hardware random number generator? Means you have seen some of the passwords are being generated based upon the mouse. You have to keep on moving, rotating mouse, and the motion of that mouse and rotation speed of the mouse and the location at which the mouse is going. All these features are being calculated together, and a random value was being generated to store and secure a key, or some value was being generated. So this is how the random hardware was being read it out and generated some output. And thereafter you have polynomial time problems. So we will discuss first polynomial time problems. So it basically contains all the decision problems that could be solved in deterministic time. Means there is a fixed time to solve them, and there is fixed polynomial time, and the amount could be solved in polynomial time. We'll see what are these polynomial time and how they happen to be. Thereafter, these problems may be P complete. What is P complete? P complete is means the class of problems, that there are various class of problems and they have what they belongs to same category, that they could be solved in polynomial time. So they are called as P complete. Then the class of computational problems that are effectively solvable and tractable. What is tractable and effectively solvable? Means you can solve an algorithm on a given computer, and then you can solve, say it is easy to solve it, and tractable. Then class P basically typically define some of the tractable problem, and they are what sequential algorithms. So these class P are basically sequential algorithm. Means these problems happen to be occur in some sequence. Means step 1, step 2, step 3, step 4. So these are the class P problems. Then in reality, there are some problems that can't be solved in polynomial time. So in reality, there are many problems that can't be solved in polynomial time. So we'll see these problems. What are these problems? Then the polynomial time problem further discussed. Whatever you do the programming, you create some function, you create some method in some polynomial time. So these are having some constant time, and that could be solved in a polynomial time. Means they are not exponential. They are having some 2 to the power. They are having some n to the power 2, some n to the power 3. So this is what we had seen till now. Then entire algorithm would take polynomial time. So this is what we can say you are doing programming for polynomial time, and this is what desirable in computer science. Then some problem polynomial problems algorithm that we had just seen discussed: minimum spanning tree, Kruskals algorithm, order of e log v, Prim's algorithm, order of e plus v log v, shortest path algorithm, that is disaster's algorithm, e log v time takes it, Bellman Ford, it takes e dot v algorithm, e dot v times. Then you have NP naming convention. So some of the problems are said to be hardest, means they are NP hard, and it's very difficult to solve them. Thereafter you have some hard problem that is NP complete, means they are relatively less hard. So this is NP complete, less hard problem. Then medium hard problem, medium problems. So these are just NP, and then some of them are easy, means easy to solve. These problems are solvable in polynomial time. Then what are the order of n, means n could be input, so there are n inputs are being given, and it will take constant time when it is big O of 1. It will take or big O of log n, then it is said to be logarithmic time. Order of n, it is said to be linear time. Order of n square, it will be said to be quadratic time. Order of n to the power k, it is said to be polynomial time. Order of k to the power n, now it's exponential. Means this is what it is. NP means non-polynomial, and it takes time. So it is exponential time, means non-deterministic polynomial. This is k to the power n, and n factorial, even much larger values in the factorial times. Then you have naming convention like NP hard could be defined as class with at least as hard as NP hard hardest problems. So hardest problems in the NP are said to be NP hard, and there are even much larger harder problems as compared to NP hardest problems. So this is the diagrams you have to understand it. This Venn diagram, that there are NP hard problems that actually been very difficult to solve. How they are being difficult to be solved? So basically, what it means. So we'll start with this NP easy. So NP easy means it is at as most hard as NP, but not necessarily NP. Means it is hard, but not as hard as other NP problem. So it's relatively easy to solve. So it's NP easy. Then class of computational decision problems that could be given either yes solution, or it can be and can be verified in some polynomial time. So NP are the problems that are having computational decision problems. What are the computational decision problems? They are like, there are very difficult to generate some solution of that algorithm. Means it's very difficult to generate some algorithm of that problem, but you can verify the solution. Means if you have given some solution that this has to be solution of this algorithm, then you can verify that either this is solution or not a solution. So this is NP problems. Then NP complete is basically some of the hardest problems of NP. So it is topmost region of NP. Means some of the hardest problem of NP are said to be NP complete, and each NP complete problems must belongs to NP. So NP complete problems belongs to NP. Then we'll discuss about NP and NP problems. First, we'll see what is deterministic algorithm and what is non-deterministic algorithm. So deterministic means you have fixed set of steps and generating accept or reject. But in non-deterministic, you don't have fixed set of step. You can either generate accept over here, or you can generate reject over here, or accept over here, or anywhere else. So it's non-deterministic. So NP stands for non-deterministic polynomial time. where non-deterministic means random guessing, means here it will be producing result, here it will be producing result, here it will producing result. So it is luckiest possible guess, means whatever prediction you'll take and the result would be generated, it's fine. Then complete means, what is complete? NP complete means a set of class, means a particular class are being defined to say it as NP complete. So complete refers to the same complexity class. Means how much complex it is. Then P versus NP means polynomial time versus non-deterministic polynomial time could be determined as NP is like a problem that can be verified in polynomial time, means that whether the problem can be solved in polynomial time. So these are the, based upon these two questions we can describe and create difference between polynomial and non-deterministic polynomial. Whether the problem can be verified in polynomial time. If yes, then it belongs to NP. If whether the problem can be solved in polynomial time, if it can be solved in polynomial time, then it is directly P, means polynomial time. If it can only be verified in polynomial time, then it is NP. It turns out to be, means world would mostly accept that P is not equals to NP, means this is real condition, that in reality there are some easy problems, there are some hard problems, there are some very very hard problems that don't have any solution. So these are like that, means polynomial time problems can't be equal to non-polynomial times, and this is what the world actually believes. And this whole domain and field of computational theory believes on and works on P is not equals to NP, means this is what we aim to achieve, that there are some easy problems, some hard problems, there are some medium problems, there are some very very hard problems. So this is what P is not equals to NP. Then there are various problems in NP that have hardest to be compute but can be verified. So there are various problems in NP that are hard to compute and easy to be verified. Means you can have solution, then you can verify that this is the correct solution or not a correct solution. Then you have NP problems that cannot be solved in polynomial time. That is what we are just discussing. NP problem can't be solved with n polynomial time. Means they don't have algorithm for solving it in the polynomial time. Then you have, but on contrast you have some solution of that algorithm and you can verify that solution, whether that solution is correct or not for that algorithm, for that problem set. So it can be done in polynomial time, that is NP problem. Then you have NP complete, as we just discussed, that non-deterministic polynomial time, means non-deterministic means random guessing. Complete means a particular class of complexity is defined for this NP. Then NP complete means have the definition when you have some brute force search algorithm. Means brute force is very very time consuming. So you still have some brute force time consuming algorithm to solve it, as well as you have some correctness algorithm, means you have some algorithm to check that the solution was correct or not in some polynomial time, means you can verify that algorithm very quickly, means results are being verified very quickly. Then the problems can be simulated on any other similar solvability problem. So one NP complete problem can be transformed or reduced or simulated to another NP complete problem because they both have similar solvability problems. Then you have the NP complete problems, like it can be verified quickly. So NP complete problems can be verified very quickly, but there is no known solution to find the solution of that NP complete problem quickly. Means there is no polynomial time solution. Means it's not findable way to find some solution for those NP complete problems. Then this is the NP hard problem structure. Means all the top thing that we had discussed just now. This is NP hard. And you remember that we said that NP is not equals to NP. So this is what world believes, and this is a real situation that some are the easy problems, some are the medium problem, some are the hard problems, some are very hard problem. But what if there is no easy and no hard or no nothing like that? So it will become what everything could be solved in brute force, and you have some architecture looking and set would looking like this. Means polynomial time would be equal to non-polynomial time, and non-polynomial time would be equal to NP complete problems. Then you have at least as hard as some hardest problem in NP. So these NP hard problems are very very hard problems of this region. So NP hard is basically hardest problem of NP. So you classify those hardest problems of NP as NP complete, and these are the part of NP hard. Then you might have some polynomial time algorithm that can actually solve some NP hard problem, but it might not be known today, but it may be known in future. So this polynomial time problem may not be known today for that NP hard problem. But it may be possible that somebody like you or some innovator and you write an algorithm to detect and solve that NP hard problem in polynomial time. Then you are the innovator and inventor. And now you had discovered that polynomial time to solve that NP hard problem. Now, in that case, it will not be the NP hard problem. It will be a normal polynomial time problem. For example, many years ago, it's very difficult to find prime numbers. But recently, IIT Kanpur had discovered an algorithm and written an algorithm which can solve and find the prime in polynomial time. It's the research paper is also named as primes in P. So that is what the invention level. So before that publication of paper, before that 6 line algorithm, people say thinks that means a scientist of computation theory thinks that it's very hard to find prime number in polynomial time. But when this 6 line algorithm came up and IIT Kanpur research was successful, then the computational theorist will start thinking that yes, we can find the polynomial time, we can find prime number in polynomial time. So this is what it means by there might be some polynomial time algorithm for NP hard problem, but might not be discovered yet. Means today it's not discovered, so it's a NP hard problem. Then the examples of NP hard but not NP complete means it is at the topmost part, this part, NP hard part. What are these? Halting problems means you have a given problem and its input, and you have to detect whether it will run it forever or not. So is it possible to run it forever or not? So it's NP hard problem. Then you have traveling salesman problem. We'll discuss these two problems in some detail, that traveling salesman and halting problem. Thereafter, this right hand side part of this figure is like imaginary. If you have this P equals to NP means you have easy problems, medium problem, harder problem, or all are belonging to the same category, means all could be solved in polynomial time. Then what will happen? This whole set will become set will squeeze and will become same set, and you'll have P equals to NP means everything will this thing will become polynomial, and non-polynomial will be the part of polynomial, and this non-deterministic polynomial complete and non-deterministic polynomial and polynomial would all belongs to the same set. Means all these problem could be classified in same set. Then next you can have reductionism. So we'll discuss this reductionism in the next class. I hope that you all had enjoyed this part of introduction to the PNP and NP complete NP hard problems. So we'll discuss in the next class in detail this reductionism and other part of this